Hello. In this video, we are going to do lecture 22, the first part. In the previous lecture, we discussed Laplace transform of some elementary functions. And in this lecture, we will see how to use the Laplace transform to solve initial value problems, differential equations with initial conditions. Okay, so this is especially helpful if we have a linear differential equation and the differential equation is for a function. We are trying to solve it to find the solution function. And usually we denote the function by y and the independent variable, let's say t, with initial conditions. What we do is we can take the Laplace transform of both sides of the equation. And in this way, we obtain another equation. And hopefully, simpler, more simple, let's say. Another more simple equation. But now our equation is going to be for, since we are taking the Laplace transform, the function is going to be a different function. It's going to be the Laplace transform of our unknown function, yt. So in our equation, first of all, this is going to be kind of standard. We represent the unknown function in our differential equation with the small case letter y, and its Laplace transform we denote with uppercase y. So the function in our differential equation is a function of the variable t, but its Laplace transform is a function of s. And this new equation, we will see in examples, is going to be a linear equation. We can solve it for the function capital Y of s. When we solve this equation, for capital Y, so we are going to obtain an expression for solving this equation. Means we are going to isolate the function capital Y on one side of the equation and obtain an expression in S for this function on the other side. We can find our solution, small y of t, solution of our differential equation, by going backwards. So by computing the inverse of the Laplace transform of capital Y. I tried to talk about this in the beginning of the previous lecture. So in the t space, we have an equation for yt. We apply the Laplace transform. So we go into the S space, and in this space, we have another function, capital Y. So if we solve this function, and from this expression, we go backwards. So this is inverse Laplace. So given the equation, apply Laplace to get equation for capital Y of S, solve that equation, and then to the solution, apply inverse Laplace to find the solution of our differential equation, of our initial value problem, really, because we will see in a minute, in order for this to work out, we need initial conditions. Okay, so since we are going to apply the Laplace transform to a differential equation, in the differential equation we have derivatives. So to do this, we need to see the effect of the Laplace transform on derivatives. So basically, the question is then, in order to continue, we need to answer this question. If the function f of t is differentiable with derivative f prime of t, and if we know the Laplace transform of our function f of t, remember we denote this by capital F of S, what is the Laplace transform of the derivative? Okay. So we are trying to find, I'm not going to do this as a theorem proof thing. You can see the actual statement of the theorem and the actual line of the proof in the lecture notes I'm going to share on MetroClass and also in your book. So I'm going to proceed informally. We are trying to find the Laplace transform of the derivative. So what's the definition? The integral from 0 to infinity e to the minus st times the function. Now what I want is to use the Laplace transform of f. So in this integral, instead of f prime, I want f. And to reduce f prime to f, what I do is use integration by parts. Integration by parts. So integration by parts means I need to choose u and dv. So for u, I choose the expression e to the minus st and dv as f prime t dt. Then what is du? I take the derivative of e to the minus st with respect to t. My integration is with respect to t, so du is, I need to differentiate this function with respect to t and multiply by t. So when I differentiate with respect to t, I get minus s e to the minus st dt. And what about v? To get v, I need to do the integration, but integral of the derivative is the function. So now, this integral, first of all, I write it as a limit. M goes to infinity of integral from 0 to m. And for this integral, I used integration by parts. So what is integration by parts? I have u times v. So v is ft, u is e to the minus st ft t from 0 to m minus integral from 0 to m of v times du. But du have the coefficient minus s, so the coefficient of the integral becomes plus s, integral from 0 to m, e to the minus st, f of t now. V is f of t. So I have this integral. So we have limit as m goes to infinity. If I substitute m for t, e to the minus sm, f of m, minus, then we substitute 0, e to the 0 is 1, we have f of 0. And plus s times, when I take the limit as m goes to infinity, this becomes the integral from 0 to infinity. So I have this limit, e to the minus sm, fm, minus f of 0. F of 0 is some constant value. So the limit of the constant is constant. So I have this constant term plus s times, and this integral now, 0 to infinity, e to the minus st ft, is the Laplace transform of the function f. So I need to somehow take care of this limit, but remember from last time, to make sure that a Laplace transform of a function exists, in this case, we are assuming Laplace transform of the function f exists, is capital F. We have absolute value of f less than or equal to a constant k times e to the at for some constants k and a, so that Laplace transform of f exists, which is f of s. In this case, this limit is going to be 0. For s greater than a. Of course, it depends on the value of s. I'm going to replace my function with, okay, I need to take the absolute value, but suppose it's a positive function, or take the absolute value. Then instead of the function f, I have this function e to the at. So when I combine it with, so I'm looking at f of m. So I have e to the a times m. And multiplied by, in the limit, it's multiplied by minus s times m. So we are going to get the limit similar to what we did in the previous lecture. So as long as s is greater than a, this limit is going to be 0. So what is the upshot then? And this interval, remember when we take, when we have this inequality, the Laplace transform of my function exists for s greater than a. So this condition comes from the condition, the interval for the Laplace transform of the function f. So it's nothing extra. It comes together with the Laplace transform of f. So basically, what is the upshot, the summary? If the Laplace transform of the function f of t is capital F of s for the values of s greater than some number a, then the Laplace transform of the derivative is minus f of 0 plus s times Laplace transform of f. So minus f of 0 plus s times capital F of s. Okay, so this is the basic result that we are going to use. Okay, but in a differential equation, we have higher order derivatives, not only the first derivative, higher order derivatives. So if f of t have derivatives of all orders, and they satisfy this condition. Derivatives of all orders, and they all, and okay, oops, what am I doing? Okay, and if they all satisfy the condition, absolute value less than or equal to some k times e to the at. Okay, I should put this parenthesis here. This condition is going to be, this is a little formal detail we need to put in to make sure that we can use the formula. But in our case, the solution of our differential equations always satisfy these properties. At least in our examples, they will always satisfy these properties. So this is going to be automatic for us. We are not going to check this condition. We will, how shall I put it? It is true that our solutions satisfy this condition, but we are not going to dwell on that. We are not going to go into the details and say that they satisfy the condition and so on. We will just use this formula, okay? So if our function have derivatives of all orders, which satisfy this property so that the Laplace transform exists, then how do we compute, for example, the Laplace transform of the second derivative? Okay, so I'm going to use the above formula because then we use above formula repeatedly. So the second derivative is the derivative of the first derivative. So we use the above formula where f is replaced by f prime and f prime is replaced by f double prime. So this is minus f prime 0 plus s times Laplace transform of f prime. But again, by the above formula, Laplace transform of f prime is minus f of 0 plus Laplace transform of f. So we have minus f prime 0 minus s times f of 0 plus s times capital F of s. What about the third derivative? Third derivative is the derivative of the second derivative. So by the formula, let's call the main formula by star. So by star, this is minus the second derivative at 0 plus s times the Laplace transform of the second derivative. But the Laplace transform of the second derivative, the above formula, minus f prime 0 minus s f of 0 plus s capital F of s. So we have minus f double prime 0 minus s f prime 0 minus s squared f of 0 plus s squared capital F of s. So I hope that you see the pattern here. So in general, the nth derivative, the Laplace transform of the nth derivative, we start with minus n minus first derivative at 0, minus s times n minus second derivative at 0, minus s squared times n minus third derivative at 0, minus, we keep going until we reach minus f of 0, and the power of s is going to be power of s in front of f of 0 is going to be 1 less than the power, the degree of the derivative we are trying to compute. So s to the power n minus 1 f of 0 plus s to the n minus 1 capital F of s. Wait. Okay, I made a mistake, right? Okay, so let's go back. In computing the Laplace transform of the second derivative, I used the formula star wrong. I have another s here, so this becomes s squared. So when I use the formula here, this is s squared, so this should be s cubed, so this should be the last term should be s to the n fs. Okay. We will see examples, but let me check my final result. Yes, this should be it. So we start with, let's say we are trying to compute the Laplace transform of derivative of degree n. Then we start with derivative of a lesser degree at 0, and then we keep putting powers of s and with the minus signs. And once we reach f of 0, then the next term is plus. We again increase the power of s by 1, and we have the Laplace transform of the function f. It will be more clear on examples. So let's say we have a differential equation, second derivative of y minus 5 times y prime plus 4y equals cosine 3t. But we need initial conditions. You see why we need the initial conditions. For the first derivative, I need to know f of 0. For the second derivative, I need to know f of 0 and f prime 0. And in general, for the nth derivative, I need to know f of 0, f prime 0, up to n minus first derivative of f at 0. So this is the highest order of the derivative of y is 2, second derivative. So I need y0 and y prime 0. And let's say y0 is 2 and y prime 0 is 0. Under these conditions, let's find the Laplace transform of the function y. I don't know what the function y of t is. All I know is that it satisfies this differential equation, y double prime minus 5 times y prime plus 4y equals cosine of 3t. And also it satisfies these initial conditions. At 0, the value of the function is 2. And again, at 0, the value of the derivative is 0. And using this information, I want to find the Laplace transform of the function. So what we do is we take the Laplace transform of both sides of our equation. Okay, so by linearity, on the left side, I have Laplace transform of y double prime. minus 5 times Laplace transform of y prime plus 4 times Laplace transform of y. And on the right side, we computed the Laplace transform of cosine AT last time. Remember, it is S divided by S squared plus A squared. And A, the number A, the coefficient of T inside cosine is 3 now. So we have S squared plus 9. And this, remember, this works for S greater than 0. Not greater than 3 or anything like that, but for every positive S. Go back and check your notes from last time. Okay. Now, for Laplace transform of y double prime, I'm going to use the formula we obtained above. So for the second derivative, Laplace transform with second derivative, I have minus y prime 0 minus s times y0 plus s squared times Laplace transform of y. Minus 5 times, and what is the Laplace transform of y prime? Minus y0 plus s times Laplace transform of y plus 4 times Laplace transform of y. S over s squared plus 9. Laplace transform of y, I denote by capital Y. Now, y prime 0, I given to be 0. S times y0 is given to be 2. S squared, and Laplace transform of y, I denote by capital Y. Minus 5 times, minus y0 is 2, plus s times the Laplace transform, I denote by capital Y, plus 4 times Laplace transform. Let me continue over here. So I have minus 2s plus s squared capital Ys plus 10 minus 5s capital Y of s plus 4y of s equals s over s squared plus 9. So let's take this minus 2s plus 10 to the other side, and let's combine the coefficients of capital Y. I have s squared minus 5s plus 4 times capital Y of s, and the other two terms, I take them to the other side as plus 2s minus 10. And finally, to find my function y of s, I need to divide by this coefficient, so it goes to the denominator. The first term is going to be in the denominator s squared plus 9 times s squared minus 5s plus 4. And then 2s minus 10 divided by s squared minus 5s plus 4. So you see, you have a differential equation and you have initial conditions, but once you apply the Laplace transform, your equation in the function capital Y becomes very simple, linear equation. Of course, because the original differential equation is linear, when we apply the Laplace transform, we get a linear equation in capital Y. So we can easily solve it to find the Laplace transform capital Y. And now, of course, okay, we answered this question, but we haven't solved the differential equation yet. To find a solution for our initial value problem, we need to find the function small y of t, whose Laplace transform is this function, capital Y of s. So we need to apply inverse Laplace to this function. First, let's do another example to find this Laplace transform function, and then we are going to talk about finding the inverse Laplace. So let's do another example like this. So example 2, suppose the fourth derivative of y plus y equals e to the minus 2t. Y0 is 1, y prime 0 is 0, y double prime 0 is 2, and the third derivative of y, it's 0, is 0. Since in the differential equation I have the fourth derivative of y, in initial conditions I need up to the third derivative of y. Again, the question is the same. Find capital Y of s, which is the Laplace transform of our function. So again, we take the Laplace transform of both sides of the equation. Okay, the fourth derivative of y, by our formula, it is, we start with minus the third derivative, it's 0, minus s times the second derivative, it's 0, minus s squared times the first derivative, it's 0, minus s cubed times y, 0, plus s to the 4 times Laplace transform of y. And then we have plus Laplace transform of y equals Laplace transform of e to the minus 2t. Again, remember from last lecture, in general, Laplace transform of e to the at is 1 over s minus a. So 1 over s minus 2. So 1 over s plus 2. And this is for s greater than minus 2. Okay, third derivative of y at 0 is 0. Second derivative is 2. First derivative is 0. Y0 is 1. And then s to the 4 plus 1 times Laplace transform of y. Remember, y of s, 1 over s plus 2. So s to the 4 plus 1, capital Y of s, equals 1 over s plus 2. I have minus 2s. If I take it to the other side, it is plus 2s. And I have minus s cubed. On the other side, it becomes plus s cubed. So finally, to find y of s, I divide by s to the 4 plus 1. So 1 over s plus 2 times s to the 4 plus 1 plus 2s plus s cubed over s to the 4 plus 1. And this is for, remember, s greater than minus 2, because on the other side, to find Laplace transform of cosine 2t, we need to take s greater than minus 2. Okay, so I hope that it's more or less clear how to find the Laplace transform of our function. Now, in order to solve the differential equation, we need to find the inverse Laplace transform. But we find the inverse Laplace transform. Again, I'm not going to go into the theoretical details. To find the solution, yt, we need inverse Laplace transform of capital Y of s. So we denote it like this: small y of t is inverse Laplace of capital Y of s. Okay. To do this, we use this important fact. Since the Laplace transform is linear, its inverse is also linear. So this is the main thing we are going to use. And as you see from the examples, basically our function, capital Y, is going to be a rational function, a polynomial in S divided by another polynomial in S. And we are going to write it, use partial fractions to write our function. So when capital Y is a rational function, we first break it up. We first break it up into its partial fractions. Partial fractions, and use the linearity of inverse Laplace. Okay, so let's do some examples again. Let's find the inverse Laplace of the function 1 over s squared minus 5s plus 4. So to break it into its partial fractions, first we need to, I don't need a parentheses here, we need to factor out the denominator. In this case, we can factor it out as s minus 1 times s minus 4, right? So I try to write this as a number a over s minus 1 plus a number b over s minus 4. You remember this from integration using partial fractions, how to find a and b. On the right side, we get the common denominator. So we multiply a with s minus 4 and b with s minus 1. So we get the denominator s minus 1, s minus 4. So the numerators have to be equal. So a times s minus 4 plus b times s minus 1 should be 1. So that means a plus b times s minus 4a minus b should be 1. This means a plus b should be 0, and minus 4a minus b should be 1. So we need to solve these two equations to find a and b. From the first equation, we have b equals minus a. And if we use it in the second equation, we have minus 4a minus minus a equals 1. So minus 3a equals 1. A is minus 1/3. B is 1/3. So my function is 1/3 times, b is plus 1/3. b is the coefficient of s minus 4 minus 1 over s minus 1. It's minus because a is minus 1/3. And whenever you find your coefficients and write your rational function in partial fractions, always check your answer. The right side, is it equal to the left side? So quickly do the computation, see if it's right. So s minus 1 minus s minus 4 is 3 over 3 is 1. Yes, it is correct. So the Laplace inverse, then, using the linearity, 1/3 times Laplace inverse of 1 over s minus 4 minus Laplace inverse of 1 over s minus 1. Now, 1 over s minus 4 is the Laplace transform of e to the 4t, right? And 1 over s minus 1 is the Laplace transform of e to the t. That means Laplace inverse. So Laplace inverse of 1 over s minus 4 is e to the 4t, and Laplace inverse of 1 over s minus 1 is e to the t. So Laplace inverse of our function, 1 over s squared minus 5s plus 4 is 1/3 times e to the 4t minus e to the t. So this is how we find the Laplace inverse. Now, more examples. No, okay. So then we are going to do examples on actually solving initial value problems. So we connect the two parts. Given the initial value problem, apply the Laplace transform, find capital Y of S, and then apply inverse Laplace transform to solve the equation. And this is going to be in the second part of this lecture. So that's all for now.